deadline has been moved up 3 weeks. The schedule as planned says you cannot possibly make it. So what do? This lesson is built around exactly that critical situation. In this first slide, we set the stage for schedule compression techniques. We will cover the 2 primary compression techniques, how to analyze the cost implications of each option, and how to document your decisions so they stand up under scrutiny. Before we get into the techniques, make sure you have this framing right. Compression is not about working harder or hoping things speed up. It is a deliberate trade-off. You choose to spend something money, risk, or quality margin to buy back time. That mindset shapes every choice we discuss. We have 2 fundamental strategies: crashing and fast tracking. Crashing pours extra resources into critical path activities to shorten their duration. Fast tracking overlaps activities that were originally planned to run in sequence. Both recover time, but they work differently and carry different risks. The core skill of this lesson is knowing which strategy to use when.
Crashing a schedule means piling extra resources onto a critical path activity. You add more labor, more equipment, or extra shifts to shrink how long that task takes. But here's the catch: crashing only helps if you're working on a critical path activity. Speeding up a non-critical task does absolutely nothing for your finished date. So in P6, your first step is to identify those critical activities, then you model the additional resources. Here's the crashing process in P6. Start by filtering for critical path activities using the total float equals 0 filter. Then rank those activities by crash cost per day saved. You want the cheapest time first. Next, go into the activity's resource assignments and increase units or add a new resource. Finally, recalculate the schedule to check if the end date moved and if a new critical path emerged. That leads directly into crash cost per day. This formula is the engine of crashing decisions. First, take the cost difference between the crashed and normal scenario, then divide by the days you recover, the normal duration minus crash duration. The result tells you exactly how much each compressed day costs. When you have multiple crash candidates, rank them by this ratio and crash the cheapest ones first. That's how you minimize total compression cost.
Fast tracking means you start a successor activity before its predecessor is fully complete. In P6, you apply a negative lag, called a lead, to the relationship between 2 activities. The schedule compresses because work now runs in parallel. So the trade-off is rework risk. If the predecessor changes, any work already done on the successor may need to be scrapped and redone.
Fast tracking's attractive, no upfront cost. You're not adding resources, just reorganizing the sequence. But the rework risk is very real. If, for example, the design you overlapped with procurement changes late, you may have ordered the wrong materials. Use fast tracking only where the predecessor's output feeding the successor is stable and well-defined early in the work. If you have multiple compression options, this matrix helps you rank them. Plot each option based on time recovered versus added cost. Always start with options in the bottom right quadrant. That's maximum time for minimum cost. Top right is your last resort, only after you've used up cheaper ones. In the top left quadrant, almost never worth it. In practice, you combine both techniques. Start with fast tracking because it costs nothing. Apply leads to any relationships where overlap is safe and recover as many days as you can from that. Then use crashing to close whatever gap remains, working through your ranked crash cost list from cheapest options first. After each change, recalculate the schedule in P6 and check for any new critical paths that may have emerged.
This is one of the most common mistakes in schedule compression. You crash an activity, see the end date move, and think you're done. But compression often reveals a parallel path that's now equally critical or even more critical. Always recalculate after each change and re-examine which activities now drive the end date before making your next compression decision.
Don't skip documentation. When a stakeholder asks why the budget went up or why 2 activities are running in parallel, you need a clear record. In P6, log decisions at the activity level using the notebook field. Also keep a separate compression log that lists each option, its cost-time ratio, and the decision you made. That gives you protection and a solid audit trail for the project.
Here's a compression log that gives decision makers the facts they need. For each option, list days recovered, additional cost, rework risk, low, medium, or high, and whether a new critical path shows up. The last row flags your recommendation. This format works whether you're pitching to a project controls team or a client who needs to approve extra budget.
Let's walk through an example. You need to recover 15 days. First, apply a 10-day lead between design and procurement, overlapping work that's stable enough to run in parallel. That saves 8 days at 0 cost. Next, crash the concrete pour by adding a second crew, recovering 7 more days for $12,000. Total 15 days, deadline met, cost increase documented and approved. Picture compression as a dial. One end, full scope at original pace. The other, maximum compression, higher cost and rework risk. Most projects fall somewhere in between. Your task, find the spot on that spectrum where the time you save justifies the risk and cost you take on, then document your reasoning. Here are 3 takeaways. First, crash only critical path activities, ranking them by cost per day saved. Second, fast track first because it's free, but only where overlap is safe. Third, document every decision with enough detail to defend it. These habits make your compressed schedules credible, defensible, and professionally sound.